Hello, everybody. Welcome to the Amazon Redshift Insider Series. As part of these webinars, we will share details about some of the exciting features of Amazon Redshift we have recently launched. Today, I'm going to talk about Amazon Redshift Materialize views functionality and how you can leverage it to boost the performance of your queries and simplify maintaining pre-computed tables or views. I'm Prasad Varakur, Product Manager of Amazon Redshift, and I'm joined by Christian Roming, Founder and CEO of AtLeap, which is a ETL and ELT as a service company, and our launch partner for this feature. He will share how they have integrated Materialized views into their product and have demonstrated the value of Materialized views to our joint customers. I will start with a quick introduction of Amazon Redshift and Materialized views feature and explain the typical use cases which can leverage Materialized views. Then we'll share some more details about using Materialized views and then hand over to Christian to share AtLeap's experience of integrating the feature into their product and how Materialized views have helped boost performance for our customer workloads at Axis. Axis is a leading digital marketing platform for purchasing tickets for sports and entertainment events in the United States and internationally. Amazon Redshift is the most popular and fastest cloud data warehouse. Tens of thousands of customers trust Amazon Redshift to process over 2 exabytes of data every day. Redshift provides all the great benefits and features of a modern data warehouse and gets you best value for your dollar with predictable costs. To name a few, Redshift can seamlessly scale across multiple dimensions, be it size of data or compute capacity or the number of users. For example, concurrency scaling is a Redshift feature that automatically deploys additional compute resources as needed to handle thousands of concurrent users and queries. You can also scale storage capacity using Redshift managed storage and expand to exabytes of data in your data lakes using Redshift Spectrum and the Lakehouse architecture. Redshift is fully integrated with AWS and your S3 data lake, which can readily help you evolve analytics to various kinds of data landing in your data lake and enable data sharing, streaming, machine learning, and AI use cases without requiring a re-architecture. Redshift is easy to manage, provides AWS-grade security with key management services, encryption, and VPC support, and is compliant with various certifications such as SOC, PCI, FedRAMP, HIPAA, etc. Redshift provides best performance. In our benchmark tests, we have observed Redshift is 3 times faster compared to other cloud data warehouses. Best of all, you get all this great functionality for one low price. With usage-based pricing, you can start with 25 cents per hour and easily scale to $1,000 per TB per year. Redshift provides reserved instances, which can save you up to 75% in your costs compared to on-demand prices. Amazon Redshift is expanding its capabilities at an amazing pace. Redshift team has delivered over 200 new capabilities in the last 18 months or so, thus continuing to give you better value for your dollar. Now coming to Materialized views. What is a Materialized view? It is a new kind of database object to consider in your database modeling that combines benefits of tables and views together. Materialized views store the pre-computed results that are defined by a select query and efficiently maintains the results. Effectively, it condenses a query with multiple joins and aggregates into a smaller result set, and the result set can be queried very similar to a table. That's where you get all the performance of using Materialized views. It is designed to get orders of magnitude performance improvement for repeatable and predictable workloads that you may have, for example, in your typical ETL or BI or dashboard workloads. So to highlight, there are three big benefits of using Materialized views. First and foremost, speeding up of the queries by orders of magnitude, especially when you have a repeatable workloads where a same query or a very similar query is executed multiple times. Say, for example, something coming from a dashboard query or reporting query can leverage Materialized views and execute much faster. And if you have pre-computed tables or staging tables or reporting tables that are maintained in your ETL or ELT pipelines, using Materialized views can simplify and accelerate the maintenance of these pre-computed tables. And finally, it can immensely help in migrating to Amazon Redshift, especially if you are using a similar functionality in the other databases. Let's look at an example. Imagine a big retail store setup with multiple store locations and sales transactions modeled as two tables. In this example, you can see a sales table with all the transactions and a store info table at different locations. If you want to find the total sales by location, say for your daily dashboard, that will need to execute a proper filter, join, aggregate query, which will filter the store info table for a specified location, say San Francisco in this example, and joins it with the sales table, right, based on the store key, and then finds the sum of all sales from stores in the San Francisco location. If we need to run this same query or change the filter to find total sales of, say, Chicago, then the query will need to go through all query processing to get the results. Performance and latency of such repeated queries can be much faster if we use Materialized views in such scenarios. In this slide, you can see a Materialized view called location underscore sales is created based on the two tables that we had. One is sales and the other is store info. Let's create the Materialized view which computes total sales for all locations. So we can query off of the Materialized view for specific locations for our dashboard. In this case, the Materialized view is based on the two tables, sales and store info, which are called the base tables for the Materialized view. The Materialized view is defined based on a select query. The query results are actually pre-computed and stored at the time of Materialized view creation. For this example, the query looks something like this. To look at the syntax, it goes like create Materialized view, the name of the Materialized view, and then you can specify physical properties like distribution key or a sort key, because you can use Materialized views to physically reorganize the data from base tables in different ways. That is one of the biggest advantages and use cases of Materialized views. And that is followed by a query, a select query, which is run on the base tables and the results of which are stored as the Materialized view. In this case, it is a aggregate query that joins both the sales and store info table and computes the total sales for each of the locations. Going back to the previous slide, you can see the Materialized view will have total sales for both the locations, San Francisco and Chicago. Now, if you want to query the total sales in San Francisco, the query is very simple. You directly query the Materialized view with a filter where location is San Francisco. Because you have all the total sales for all locations pre-computed and stored in the Materialized view, you can just directly access the results and return the results to your dashboard very quickly. This is where you get a latency boost of almost orders of magnitude. Of course, that might depend on various factors, such as how much is the reduction of your data from your base tables to the Materialized view, or how much of data is filtered through your predicates. Now that we have seen what is a Materialized view, let's quickly go through some of the top use cases which can really leverage Materialized views and boost the query performance. One typical use case is in ELT, the extract, load, and transform and business intelligence applications. This diagram shows a typical setup where you have a data warehouse, such as Amazon Redshift, which gets data from various data sources. And typically in an ETL pipeline, all the data is stored as some staging tables, and that is prepared as some reporting tables or final tables for consumption by your dashboard applications or machine learning applications. In such scenario, the staging tables are doing very similar queries as we saw in the example before, where they pre-compute or pre-aggregate a lot of data that is requested by the dashboard queries, and it is stored in pre-computed tables. So when using Materialized views, all the pre-computed tables can be replaced with Materialized views so that the data is readily available for your applications, such as dashboards or machine learning applications. Another use case which is typically used is to use Materialized views as a mechanism to store different physical organizations of your data. For example, assume your sales table, which is a big, huge transaction table with all transactions across all stores and all items. That is a big table, which is, in this example, say sorted or distributed by item key. That is the first column in the table, on the red colored table on the left side. Based on that, as a base table, I can create two Materialized views with different physical organization of data and subset of data, right? For example, the blue colored Materialized view here stores all the sales data by store, and it stores only the relevant columns that are required to do my analysis of sales by store, right? So it stores all the information about the store keys and the item keys and corresponding prices. Similarly, if there is a marketing team that wants to analyze which customers are going to which stores, right, or any analytics around that, then we create another Materialized view that is in green color here, which stores only a subset of data in columns as well as rows. For example, this Materialized view may store only S1 and S2 stores, right? And it is probably sorted by a customer key. So you can do customer analytics or customer 360 kind of applications that can really leverage this Materialized view. A third use case is to help get performance for accessing hot tables in your system. For example, assume you have a lot of readers and writers accessing this sales table. So to really scale the readers and writers and get big performance benefit for both the applications, you can create and decouple the data that is accessed by both these readers and writers as different Materialized views. For example, if the readers are basically dashboard queries here, right? If they are mostly interested in store and total sales, right, as we have seen in the previous example, that part of the data from this sales table can be created as a Materialized view, and all the traffic from the read applications can be directed to the Materialized view. And your new data ingestions or updates can continue to occur on the sales base table, right? So a Materialized view can separate and decouple the read workloads from the hot table. Now we have seen how Materialized views can help you speed up the query performance. Let's look at the second advantage, which is very, very useful in maintaining these pre-computed tables. So this is very typical in your ELT pipelines, right? Especially imagine a situation where you have created a bunch of these pre-computed tables, and if more updates and data changes are happening on your base tables, then the pre-computed tables will be invalidated quickly. So continuously, a data engineer or some team has to keep updating the Materialize views from the latest changes that are happening on the base tables. So this is called refreshing the pre-computed tables. And this is a non-trivial maintenance overhead for maintaining all these pre-computed tables. So when you use Materialize views, this refreshing a pre-computed table or refreshing a Materialize view, that effort can become much more simpler. So let's see an example. Continuing the previous example, assume the right side sales table gets few more transactions next day, right? Which are the bottom two in full blue color, right? If I get 2 more records to the base table, at that point, my Materialize view still does not reflect the new transactions that have happened. So to update all the latest changes, we can run a command called refresh Materialized view, right? So that command will incrementally identify the new data records which are added or modified on the base tables, and then update the Materialized view with corresponding changes. In this example, the query is reevaluated to incrementally identify the 2 rows that were added in the sales base table, and your Materialized view is recomputed incrementally. So the total sales for the 2 locations, San Francisco and Chicago, are updated to reflect the new transactions. It is very important to understand here the Materialized view is playing the role of a pre-computed table in parallel to the scenario where you were using a normal pre-computed table. So the maintenance boils down to just running a refresh Materialized view command, which will quickly identify the delta of changes from the base tables. The changes could be on either of the base tables, right? And it brings all those changes into the Materialized view in an incremental fashion. So that improves your maintenance performance, and it also simplifies the maintenance of the Materialized views. The refresh of a Materialized view is incremental for the most cases. It depends on various SQL elements that are used in the query that is defined to create Materialized view. Today, Amazon Redshift supports inner joins and various clauses such as having, where clause, group by clause, and all SQL expressions and functions, and aggregate functions such as count and sum, etc. So when these SQL elements are used to create a Materialized view, in all such scenarios, a refresh of the Materialized view can incrementally figure out the changes from base tables and update the Materialized view. There may be some scenarios where the incremental refresh is not possible. For example, if you have done a truncate or vacuum or alter table, in such cases, a refresh Materialized view command will fall back to a recompute refresh, which will completely recompute the contents of the Materialized view. We provide 3 system tables that can help you understanding various information and the state of the Materialized views. You can refer to documentation to get more details on structure of these system tables. STV-MV info is a table that contains a row for every Materialized view, and whether the data in the Materialized view is stale or it is up to date from all the latest changes from the base tables. STL-MV state is a table that contains a row for every state transition of a Materialized view. And then we have STL-MV refresh status, which contains a row for the refresh activity that is happening on the Materialized view. So you can see the history of various state changes and the information about the materialized view in these tables. Finally, the materialized views can be very helpful in quickly migrating to Amazon Redshift if you are using a similar functionality in the other databases. Now that we have seen how materialized views can really help boost the performance of your queries in predictable workloads such as in ETL BI pipelines, let's see a real example how our customers are seeing the value of materialized views. I invite Christian Roaming from Atleap, our launch partner, to showcase how they have leveraged the feature and integrated materialized views into their product and helped our common customers to really see the benefit of materialized views.
Thanks very much, Prasad. So Atleap is an ETLT tool built for AWS, and our customers use Atleap to build and manage Redshift warehouses and S3 data lakes. In Atleap, we have a feature that lets users combine data from multiple Redshift tables and create models that they can use for analytics. To do this, users specify a select query, which Atleap then wraps in a create table as, or CTAS for short, in order to create a model table. Now, it turned out that Redshift's new Materialized view feature is a perfect fit for Atleap models. And I want to show you how this works and how Materialized views improve performance. So first, I'm going to demonstrate Atleap models with an example, and then I'm going to show you how I'm going to show you real data from an experiment we ran with one of our customers, Access. So first of all, here's an example. This is made up, but both the data sources and the data are representative of use cases that our customers have. So here I have a web store where I'm selling products. And there's a MySQL database that stores information about my users and purchases they've made in my store. I'm also tracking interactions with my web store. And these tracking events are stored in their raw JSON form in files in an S3 bucket. And now I'm using Atleap to ingest both of these sources into tables in my Redshift warehouse. And this way I can run analysis on the data in order to understand user behavior and increase revenue. Once the data is in Redshift, I'm using Atleap models to speed up the queries so I can get results faster and make my analysis interactive. So let's look at how that works. One of the questions I'd like to answer is this. When a user comes to my web store, what are they spending on average? Let's look at the top users in terms of spend per login. So to get that, I'm joining the tables containing information about purchases and items to get the total spend per user. Then I'm joining that to my events table, actually the events table containing just login events. And then I'm basically dividing the spend by the number of logins to get the spend per login for each user. So let's run that and get the top 10 users in terms of spend per login. All right, so the query is done. It took about 30 seconds to run. And that's not bad, considering I have hundreds of millions of events in this login events table. But ideally, I'd like these types of queries to be interactive. So I created a materialized view on top of this event data that pre-aggregates the logins by user. So here's the same query again, but this time using the logins by user materialized view. So I'm going to run that. And notice in this case, the query took just 1 second to run, so that's much better. Now let's see how I can create and manage this materialized view through Atleap. Here in my Atleap dashboard, I have pipelines mirroring data from the MySQL web store database into tables in Redshift, and also a pipeline that's parsing and structuring login data from S3 and bringing that into a table in Redshift as well. Now let's create the model to aggregate the event data. So I'm going to click Create. I'm going to pick Redshift where my data is stored. I'm going to create a model. So here's the query. I'm selecting events. Basically, I'm selecting my login events, and then I'm joining to the user table and aggregating by user ID. Notice that Atleap recognizes these these two tables as ingestion pipelines. This will let Athlete trigger updates to the model whenever there's new data coming in from either source. Next, I can choose to create a materialized view or a table in Redshift. I'll pick materialized view this time, but I'm also going to create one based on a table so that I can show you the difference in update times. I'll give my materialized view a name here, logins by user MV demo, and user MV demo. This is just a name so I can refer back to the model later in Athlete. I'll have updates triggered whenever data in either of the two dependency tables changes, and no scheduled updates beyond that, since I'm not using any other tables in my model query. So let's get that created. All right. Next, I'm going to do the same with a model based on a table. All right, so that's great. So now I got my two models here, one based on a table and one based on a materialized view. Now, as new data is coming in through my event stream, Athlete is updating the models in Redshift. For my model that's based on a table, this is done by running a create table as query. As you can see, this takes some number of seconds, in this case 43 seconds every time. Now, with my materialized view-based model, it only takes a few seconds for each update. And that is because Athlete is using a refresh materialized view statement under the hood, and updates are incremental on the Redshift side. This is great news because it means my model's data is more up to date and fewer Redshift cycles are spent updating it over time. We ran an experiment with one of our customers, Access, on one of their Athlete models. One of the tables that they used with this model stores events, just like in our previous example. It has over 1 billion rows, and that number is growing by about 4 million every day. Now, with a CTAS-based approach, every refresh of the model was taking over 6 minutes. When we switched the model to use materialized views instead, each refresh took under a minute. So this is almost an 8x speed up. We also looked at how this number changes as the underlying events table is growing. So here you can see the number of events in the table on the x-axis and the refresh time in seconds on the y-axis. And the yellow line is showing the refresh times with a CTAS-based approach. As you can see, it grows about linearly, and that's about what you'd expect given that Redshift has to do a full table scan every time. Now, look at the update times for the materialized view. It's almost constant, and that's because Redshift is taking advantage of the incremental changes to the table. And that's great because it means that for Access, as they're ingesting more and more data into this events table, they don't have to worry about updates to the model slowing down or using more Redshift resources. That's all I had. Thanks very much.
Thank you so much, Christian. That was great to see the performance at Athlete and Access. And I hope, all of our customers get a lot of benefit from the Materialized Views functionality. Hello, everybody. Just to summarize this session, we have seen what are Materialized Views and how they can help you combine the benefits of tables or the create table as version of tables to create the PreComputer tables and the views. So basically, Materialized Views help you compute once, pre-compute once, and then use the pre-computed results multiple times. And that brings you efficiency for your predictable and repeated workloads. Typically, this can be used to maintain multiple physical organizations of data, and then boost query performance either by accessing the pre-computed results, and it also simplifies the maintenance of pre-computed results. To look at the syntax, it's very simple to create a materialized view, very similar to the ctask command. Just create materialized view, give a name, and give a select query that can include inner joins across multiple tables and aggregates and where or having and other query classes. And to access the data in the materialized view, just run a SQL query and reference the materialized view like a table, and then you can write any SQL query on the materialized views. As new data gets updated and inserted into the base tables, the materialized view can get stale. So in such cases, you use a refresh materialized view command to bring the content of materialized view up to date to contain all the latest and greatest data from the base tables. So this can help you with the performance and simplification of your pre-computed results. Here are additional resources to learn more about materialized views. Reach out to the documentation for all the latest new additional features added to the functionality. And the 3 blogs explain in detail various steps to create materialized views and use them in different use cases. Please check out all other great videos about the exciting new features in Redshift in our webinar series.